Hi everyone, my name is Vaibhav. I am a 6-year PhD student, and today I'll be talking about our research titled AI-RISC, and we'll be specifically focusing on the custom extensions to RISC-V for energy-efficient AI inference at the edge of IoT. This work has been done at High Performance Low Power Lab and all of our collaborators at University of Virginia, and my advisor is Mr. Stan. So we're talking about edge AI here. So I think the first question that comes is like, why do we even need edge AI? Because all of you will say, okay, we have the series, we have the Lexus, it works pretty fine. Why do we even care? But the thing is, all of that processing is not happening on the edge hardware, because you put your phone on airplane mode, try to ask Siri something, she's not responding, because all the processing for Siri is happening inside the cloud. And we've seen how that kind of turns out, right? So moving AI processing to edge hardware gives us a lot of important benefits. And first benefit is latency. It helps us to enable real-time workloads, because everything is happening locally on the cloud. We save on the latency of sending the query to the cloud, to the cloud and getting a response back. And this is really important for safety-critical applications, like for self-driving car. You don't want to be taking a turn where you just lost internet and you hit somebody, because the cloud could not return things back. So we want more and more edge AI things to be happening on the devices itself. And next is quality of service for sure. Like in the example, if you're hiking in the mountains, Siri is not going to respond to anything because the quality of service is really, really poor. And then the most important thing these days is security. Sending all this data over to the cloud for doing AI inference is not the most secure, as we have seen with so many hacking attacks happening in the just past couple of years. And even if the server is secure, privacy is another big issue. So the server might be secure, but the user might not feel comfortable enough to send their private data over to the internet. But they still want to run AI inference on it. Like just an example, you might have gone out after the networking session yesterday to the bar, you've clicked a bunch of pictures with random strangers. You want to know who they are. You want AI to kind of figure out who these people are, but you don't want to jeopardize their privacy by uploading those pictures on a cloud. So edge AI gives us all these really nice benefits, and along with that comes with the benefit of bandwidth saving. So in Internet of Things, and more importantly with the new paradigm, artificial intelligence of things, we are talking about these billions of devices connected to the internet doing AI services, providing AI services. And once those billion of devices start talking to the internet, 5G or 6G, it's not going to matter. We are going to choke the bandwidth. And we see these examples in, let's say, when you go to the football stadium and watch the game. So all of you are trying to tweet, all of you are trying to give the latest updates, and there's no internet, because all those devices, when they get that densely packed in an area of single network, you're going to choke that bandwidth. And even if you don't choke the bandwidth, there's a cost involved. So if we send every image that we take to AI just to figure out that one good image which gives us actual good information, we are spending an actual dollar cost on these network communications. So edge AI processing as many things on the local devices for AI as possible saves actual money. But, so you're going to say, next question could be, okay, we want to do things on hardware. There's already hardware, there's TPU, there's so many good accelerators. What's the big issue? So the next issue is all those accelerators have been designed for big AI, for the cloud AI kind of workloads, but edge AI is very, very different from these workloads. And one of the first thing is like all these edge devices, they are kind of doing BERT, and they're doing new, like this huge language models, which are, I think, have reached almost 175 billion parameters. Edge devices are exactly the same. They're trying to scale these models down as much as possible while keeping the accuracy. So we are not talking about really small neural network models like ResNet 8, which is kind of 8 layers. And on top of it, we are doing batch size 1 applications. On the cloud, you can take, let's say, 256 images, batch them all together, and you can efficiently maximize the resource efficiency, resource utilization of your hardware. But on edge, that's not going to happen, because let's say if you are taking the example of a security camera, and if we are doing 30 frames per second, and let's say if some intruder enters, you don't want to wait 3 minutes to just tell the person, oh yeah, I was batching images, and now I see the intruder 3 minutes after, like, the robberies already happened. So a lot of the edge use cases, and similar with Siri, when somebody says, hey Siri, you want to respond right then. You don't want to batch those inputs together so that you can maximize your resource utilization of this huge accelerator that you have put for AI. So these are the kind of things that are changing towards as we think about AI hardware on the edge. And on top of that, edge devices are obviously power, area, cost limited, so that again calls for smaller accelerators. And one more thing that comes into play when we think about edge AI is, since the area is a kind of a costly resource on edge. All these devices, they need to support both AI and non-AI applications on the same hardware because they don't have the real estate to add new accelerators for every new thing that they start want to do. So like most of these edge processors, they want to support AI, but they don't have real estate area for huge accelerators to be put there. And another issue that comes while you try to do AI applications and non-AI applications on the same platform, all these edge processors, they have primitive software support. So all of them, they are really good with C, C++ compilers, but some of them support TensorFlow, some of them support TensorFlow Lite, but they don't support these wide variety of domain-specific languages, which AI software people, they are comfortable coding their languages, their applications in. So to take care of all these issues, we are designing AI-RISC, and AI-RISC essentially is a custom RISC-V processor. So we are extending the RISC-V processor with new AI instructions which are targeted towards accelerating AI workloads. And while we do that on the ISA side, on the hardware side, we are tightly integrating AI accelerators for fine-grained offloading of AI tasks because we are now talking about doing AI and non-AI on the same platform. So this workloads are going to be a mix of AI and non-AI. So we want much finer-grained offloading for these things. And these AI functional units, or the AI accelerators as we call them, they can be of any form. They can be really simple as working on simple vectors, or they could be doing matrix multiplication in this matrix AFU. And so this AFU stands for AI functional unit. So that's the kind of term we are using for these really small accelerators that we are putting inside the processor pipeline. And so we do the extensions on the ISA side. On the hardware side, we add these, tightly couple these small accelerators in the microarchitecture of the processor. But while we do that, we also realize that nobody's going to use this processor if it doesn't have software support. So on the software side, we are building the software infrastructure. So we are designing all of these three things together: hardware, software, ISA, co-design kind of a solution. And the end goal here is to support both AI and non-AI applications on the same edge processor. To further clarify this point of how this AI functional unit is slightly different from the previous AI accelerators that we have seen. So traditionally, we used to see for TPU, for IRIS, all these nice, really great accelerators that came out that kind of advanced the edge AI hardware. All of these were acted as co-processors. So they were AI processing units that were talking to the CPU over a system bus, sharing CPU resources. And all they did was the AI part of the computation. And as we advanced in the 3D memory technology, we started moving towards near memory compute. And so in 3D memories like HBM and HMC, a lot of researchers very cleverly, they put AI processing on the logic layer of the memory die. So with this near memory kind of accelerators, the system bus still remains. So the CPU was still doing a very coarse-grained offloading of AI tasks. You carve out a huge AI task, you send it over to this accelerator, and then you wait back for the results. And once we start moving forward in the last 5 years, we have seen a lot of in-memory processing. So rather than from near memory, we have started moving towards in-memory. And in-memory processing, very novel solutions, what they do, they take some part of memory hierarchy. Either they take the main memory, they take the cache, or some part of the registers close to the processor. Some part of the memory hierarchy, they are repurposed as an accelerator. And still, but the system was that's talking, like, so this coarse-grained coupling of the accelerator still stays. So we're trying to change that by moving all this AI functionality inside the processor. And so the task here is, because the workload is not that big, so that you can take the huge chunk of computation and just send it over to an accelerator. So this is finer-grained offloading of AI tasks. And the way we do that, so in this example, we started with a five-stage RISC-V pipeline, and it has the standard fetch, decode, execute, memory, and write back stages. So essentially, for the new instructions that we start adding, so these AI functional units sit in the execute stage of the processor pipeline. So the new instructions are still fetched the same way as standard RISC-V instructions. They're still decoded the same way. Once they are decoded, once we figure out, okay, this is one of the new AI instructions. So rather than sending it to the execute units of the processor like the ALU, the operands are sent to these AI functional units, which are the execute units. And in some cases, let's say if we want to add more complicated AI accelerators, which are, let's say, a processing and memory-based vector matrix multiply unit, so which has a mix of memory and execute stages. So in this case, so it sits close to the data memory, and just like the load store happens on the data memory, there are custom instructions to do load stores on this particular memory of the accelerator. So this talk is about custom extensions. So that was a brief overview of what we are doing on the hardware side. So let's talk about the extensions now. And just to give a disclaimer that we have grouped these extensions based on the AI function units which they are targeting. And all the extensions that are presented in bold have already been implemented, and whatever is not bold is still in the proposal phase. And all the instructions have been implemented in the custom 2 opcode space of the RISC-V so that we still maintain compatibility with the base RISC-V processor. So when we started doing this ISA extensions, our vision was to do these top-down kind of extensions. So these very intuitive instructions, which are like multiply, accumulate, generalized matrix multiplier, matrix vector multiplier. So all these new instructions, they directly accelerate some part of the AI workload. But as we started implementing new instructions, we also figured out that we need these bottom-up instructions that are not coming from the top-level application, but they're coming, the need for these instructions are coming from the bottom accelerators that we are adding in the processor pipeline. So these instructions are non-intuitive, but they still help to accelerate the AI on the hardware because they are directly support AI hardware. And one example is this custom load store that we have to do for new memories that we are adding. So first of all, we talk about just general extensions. So these are not essentially tied to any particular AI function unit. So these can be accelerated in a hardwired data path on the processor. And so first example is the most common example that we have seen across the board. Anyone who's trying to do this kind of work, first instruction they put is a MAC instruction. So for us, we started with that. That was kind of the proof of concept. We also emulate packed SIMD with 4 and 8 different lanes. So we are looking at adding new instructions to accelerate the quantization side of running the workload. So we usually run int8 quantized workloads. And so there is a lot of casting and recasting operations that happens because inputs are coming in int8, the outputs are accumulated either in int16 or int32. And when they go as an input to the next neuron, they still need to get back to int8. So there's a lot of casting that happens. And also there is a lot of conditional clipping. So since we are accumulating in int16 or int32, once the number goes above, let's say 128, that's the dynamic range of int8, we clip it to the max or the min. So all these conditional clipping, they have like branching instructions. There's a comparison with the maximum, and then you come back to and do the actual clipping. So we have not implemented this yet, still in the still this is only in the planned phase, but we'll be doing this sometime in the future. And so we start from example for the processor in ASIP designer, as I would be talking later on the implementation side of things. So with that, we already get useful extensions like a post-increment load store and hardware support for hardware loops. And just to give a quick overview of how, like, once adding one simple instruction can impact the top-level application performance. So in here, we are taking an example of a ResNet 8 network from the MLPerf Tiny benchmark, which has been trained on a CFAR 10 dataset. And this is an int8 quantized version of it. So we take the TensorFlow Lite implementation of this. We run it through TVM. I'm going to give more details about this in the next few slides. And we get the C source code. We pass it through the C compiler that we generated from this ASIP designer. Again, more details coming on that later. And we compile the binary. So one thing I want to show here is there is no hand coding of any kernels. Or once we add a new instruction, we don't change the top level C implementation or the neural network implementation. It still stays the same. It still is the same input. And by doing that, we see kind of almost 20% improvement. And this is with just one single MAC instruction. 20% improvement in instruction count, and almost 17% and 45% improvement with scalar and SIMD MAC operations. So that kind of shows promise. Okay, we are going in the right direction. So what else can we do? So then we started adding new instructions. So then the next AFU that we targeted was a matrix AFU. So in this, first thing that we want to do is define a matrix data type. So this is essentially a vector data type, which is, since we are working with 64-bit RISC-V, so all the registers are 64-bit wide. So what we wanted to define was a new matrix data type, which is 8 bits, 8 elements of 8 bits each. And now we can do a few different permutations on it. So we can take the same element and define a 2x4 matrix, a 4x2 matrix, and so on and so forth. And once we had this new data type, we start defining new matrix multiplication instructions. So we, like, one version is a 2x4 multiplication with a 4x2. Once after we had implemented this, we kind of went back and see how other processors are doing it. We found out ARM is doing exactly the same thing on their thumb instructions, on the neural network side instruction sets. So, and then similarly, there are matrix vector multiplication instructions and vector-vector multiplications, and this is essentially the dot product. And so one thing that we see here is there is kind of a difference between multiplying a 2x4 matrix with a 4x2 versus doing it the reverse way, because the final output that we get here is a 2x2, and if we accumulate in 16 bits each, we can still fit it in the 64-bit boundary of the RISC-V registers. But if we go do it the other way around, we cannot fit the 4x4 result in the 64-bit boundary, so we need to put the result either in 2 registers or 4 registers, depending on in which precision are we accumulating. So we are planning to add support for that as well. Next are the instructions which are related to the this processing in memory-based vector matrix multiply A function unit. So these are the simple instructions. So we define custom load stores where we take the data in and out from the processor registers, but rather than going to the data memory, it goes to the memory of this processing in memory accelerator. And then there is this actual VMM instruction. And with the VMM instruction, again, there are a few different variables on the sizes that we do. So we have defined a 1x8, 1x16, depending on what's the size of the memory that you're storing, and so instructions for that. So once we implemented this, we wanted to see, okay, now we are going to something more complex. What's the benefit? And so on a simple GMV kernel, which is a vector matrix multiply loop, you do double nested for loop to do vector matrix multiplication. What we saw was with and without these instructions, almost a 17x. And when I say without these instructions, I'm talking about RV64 IMC, so base RISC-V processor with 64 bits. And we saw almost a 17x improvement on this. And one more thing that we saw was when we coded all of this in assembly by hand, and when we did this through the compiler did 1.6x better job than us. So this kind of shows that if we want to add new instructions, we want compiler support, we want software support. We don't want to hand code everything because we cannot be as efficient as all the compiler passes that happen on the compiler side. So this further motivated us to do the hardware-software codesign methodology. And a list of the planned extensions, so these have not been implemented yet, but we are also looking at providing hardware support for activation functions, so for different activations. And also, next accelerator that we are targeting to bring inside the processor pipeline is a systolic array sort of an accelerator. So this is still work in progress. We are trying to figure out what are the new instructions that we need for this. But a few of the candidates that we have already started looking at is we need instructions to load and store data from the memories of the systolic array. And then we need the actual MAC instruction. So we are trying to figure out whether we define it as a MAC instruction, a matrix multiply instruction, or what. So these are the stuff that has been implemented yet, but will be. And this is a snapshot for all these instructions that we are implementing. This might be a slightly small, but one thing we are trying to show is in the 32-bit instruction boundary, we maintain compatibility with base RISC-V because we are not changing any of the already implemented RISC-V instructions. We are just adding instructions in this custom to opcode space. And we also maintain this 3-register rule of RISC-V instructions. So we have this one destination register, 2 source registers, and so on and so forth. But what that leads to is, so let's say we have one destination register, which is 64-bit wide, and what if the AFU is returning a result which is bigger than 64 bits? What do? We can either split the result and take it in multiple cycles, or we can define more destination registers, but then we would be deviating away from the RISC-V encoding philosophy. So we kind of did a cheat here. So what we do is we dedicate, whenever such a case happens, we dedicate a destination registers. So in the instruction encoding part, we say, okay, rather than taking the output just in the low and high side of the destination register, we dedicate 2 more registers to take this output. And the same thing is communicated back to the top level to TVM, to the software level. So software already knows that this data would be residing in a particular processor register. And we take advantage of it to get this data back. But this is just a kind of a cheat for the meanwhile till we implement support for Scratchpad. And this is again in the planned extensions. We plan to add support for Scratchpad so that we can use the Scratchpad to do this communication of operands, input and output operands between the processor registers and the different AFUs. And this would be utilized for processing in memory-based AFUs, for systolic array-based AFUs, and so on and so forth. So we've talked about the hardware side, so on the instruction side, what we are doing. But once we start adding these new instructions, we need to compile applications to these new instructions. Otherwise, they are not useful. And so this is what we have been doing on the compiler side and a lot of the issues that we have faced. And just a disclaimer, we are pure hardware designers. We have 0 compiler experience. So all of this has been done by hardware designers. So it might not be the perfect thing to do, but it's the thing that we can do. So hopefully the easier thing to do in our case. So what we do is we take a two-step compilation strategy. So on the front end, we use TVM open source compiler as the front-end compiler, and on the back end, we are using a Synopsys processor design tool called ASAP Designer, which generates a complete SDK, including a C compiler. So on the back end, we use the C compiler generated from that. And at the same time, this tool also gives a synthesizable RTL, so that's on the hardware side. The reason we use TVM is because TVM has support for these multiple domain-specific languages, so we can, rather than taking, so whenever in the past we have seen new hardwares being designed for new processor being extended with custom extensions, so we either write inline assembly-based libraries for those, and those libraries are kind of limited to a very few set of workloads that can be accelerated using that. So we are trying to remove that. We are still trying to maintain this top-level TensorFlow, Python, PyTorch level programmability for this particular processor, and that's where TVM comes into play. So we take input neural network description in any of the domain-specific languages of choice, and we use TVM to convert that down to C source code for the neural network. And then we compile it together with the C runtime wrapper and the the TVM deployment wrapper, and we send it to the downstream compiler. And this is a quick overview of the downstream compiler. So this contains a retargetable C compiler that we utilize for compiling on the backend. And this, the backend compiler has two frontends, which is one of Synopsys own native chess frontend, and another one is LLVM. So we utilize the LLVM frontend. So we kind of maintain compatibility with the LLVM community that's adding more support for RISC-V as we go forward. But compilers are hard. We ran into a bunch of problems because the C compiler that is there can easily understand instructions like MAC, but it doesn't understand more complex instructions. So what we do there is we split the loops. So let's say if we are doing a vector matrix multiply, which is, or convolution kernel, which has multiple nested for loops. So we split those loops, we take the innermost two loops, whatever we can accelerate on the hardware, and we communicate this back to TVM. So TVM does all of this. So we are not doing anything by hand later. And then while we started breaking the loop, so there were a lot of issues that started coming up. So we lost accuracy because there was wrong allocation of operands. So we broke the loop. The top-level compiler didn't understand which operand to send to which accelerator at the right point. So again, we used TVM for that. We added strided access and buffer access for the operands. And also, we defined at each stage of quantized neural network what's the data type that we support in the hardware. And so there are a few more. So I have 5 minutes left, so I'll try to move forward. So, and this is just an example. So we can take the exact same neural network defined in a TensorFlow Lite, and we can either compile it to a standard RISC-V C code, which will run perfectly on standard RISC-V, or we can compile it with the custom instructions, which will run on this extended version of RISC-V. And this is the assembly. So now all that is good. So do we get any benefits out of this? So this is the evaluation. So we have evaluated a few different benchmarks. So the baseline here is RV64 IMC version, and we also show results against a Cortex A72. So on the GMV kernel, again, we had seen this before. We get almost up to a 17x improvement, and with other instructions, 5x with the single max instruction, we improve the performance by 1.75x. But when we move on to a convolution kernel, which is more, because the GMV was written in C, was hand-coded by C, so we get huge improvements. But when we start moving to more generalized workloads, we lose this speed up, because here TVM adds a lot of wrapper code. So we accelerate only the single convolution, but there's a lot of wrapper code around it, which is not accelerated. So obviously we lose the performance. But things are not all gloomy. So when we try to run complete neural networks, like the ResNet-8 network from the MLPerf tiny benchmark, we get almost, with the processing and memory-based instructions, we get almost a 4.4x speed up over the base RISC-V, and also almost a 2x speed up over the Cortex A72 processor. And that's not just it. So in this case, I showed results for 8x8 memory in which we do the vector matrix multiplication. But how do I know if that's the best? So we also, since we are at each point, we have the software which is compatible with the hardware, with the instructions. We are able to sweep this design space pretty easily. So here I just show an example of sweeping this design space for, let's say we are doing in-memory vector matrix multiplication from the smallest matrix which can be possible, 2x2, to the biggest matrix that still fits inside the 64-bit boundary. And we get, we can run this, we can simulate this, we can test new instructions on this. And so But another thing that comes from the hardware side, okay, this is good. We are adding big accelerators, we're getting bit speedups. But what about the area? So since we get generate synthesizable RTL at each point, we can synthesize that particular version of the RISC-V processor to take area-based decisions. So rather than going with empirical decisions, okay, I want the biggest accelerator or I want the smallest accelerator, we can take decisions where we are kind of tying the other constraints as well. Okay, what if I have this much area? What would be the best accelerator? And this hardware-software co-design methodology allows us to do that. So in summary, we talked about AI-RISC, which is a custom RISC-V processor. We tightly integrate AI functional units in the microarchitecture side of the processor. On the ISA side, we add new instructions. On the software side, we are doing hardware-software co-design, where we utilize a processor design tool to generate the complete SDK for this new processor. For speedups, we get almost 16x for small kernels, 4.4x for complete ResNet 8 model from TinyML-Perf benchmark. And the most important thing here is that we are scalable. Why do I say scalable? Because let's say tomorrow if somebody comes up with this brilliant neural network model that doesn't use ReLU, doesn't use any of the matrix multiplication concepts, we can still add new instructions for that. And we can make this future-proof. So rather than changing the entire accelerator, hardwired accelerator, this solution can still be repurposed to accelerate those kind of workloads. We are flexible, so in case I want to do matrix multiplication, I can do it either in memory. So the flexibility comes from hot swapping the accelerators. So if somebody gives me a better accelerator, I can hot swap it back into, all I have to do is design the interface around it to take inputs and send outputs back to the processor, and I can add that support for that particular accelerator inside the RISC-V processor. And by doing this, we are supporting both AI and non-AI applications on the same hardware. So Jeff, do I have a minute left? So this is the last slide. So I think in the last slide, before I open the floor for questions, I have an open question for the RISC-V community. So we use a proprietary tool which is coming from Synopsys to do the backend compilation side, but can we do everything open source? Because we are taking TVM, which is open source, we are taking RISC-V, which is open source, we are trying to take hardware as much as from the open source repositories which is available. Can we do the backend as well open source? So there are options. We can do much of these things in RISC-V, GCC, LLVM, and for the simulation, we can do it on the Spike simulator, or for hardware, we can generate from Chisel. But is the community ready to add support for adding custom instructions and custom hardware in all these tools? So I think with that, I'll close my session, and I'm open for questions now. Thank you so much.
Wow, let's give a round of applause. Excellent. We're right about the end of time. I have no questions online, but I would take one from the room if somebody does have a question that they're dying to ask. No? Yes? Yes? No? I do have one that I would like sort of the answer to. You mentioned sort of the trade-off between hand coding versus putting in the specified instructions as you were doing the work. Do you have any analysis that says how long it took to design a single instruction in your instruction set, like man hours, person hours? Any feel for that?
So I think it's not as much as designing the new instruction. So if we ask this is a intelligent set of people sitting here, each one of these people will tell you, okay, this is the instruction I want RISC-V to run, because they have their own workloads. All of them know what is more important. So coming up with the instruction is not the hard part. The hard part is implementing that instruction. So putting that in the ISA, so that's still easy. You can do that in GCC, but to add hardware support. So once you have the instruction in the processor, you want the processor to support that in the hardware. So adding hardware support for that. So adding all this communication. So we are trying to reduce this communication from a bus sort of a communication where we coarse-grainedly send instructions to an off-chip or an off-die accelerator. We are doing this everything inside the processor pipeline. So that's the hard part. So, and then enabling software to run on this new instruction. So I would say the first time I did this, it took me more than 9 months just to enable one single Mac instruction all the way from TVM so that I can use the same TensorFlow code that runs on a base RISC-V and to compile it to the RISC-V with this new instruction. But after that, I learned. Now I can, and as you can see, all this design space exploration for the PIM side, which is, each of this is a new instruction of a different size. It's a new accelerator. All of this was done in a matter of hours. Because I had to generate results for a paper, so I did it in less than an hour. So yeah, so once you learn, once you have the infrastructure and methodology ready, after that it's very easy to add new instructions.
Excellent, thank you. Let's give him one more round of applause.
Thank you.